Hi everyone, and welcome to this lesson, which is an introduction to conditionals and logical statements. So first we're going to talk about converting conditionals from English to logical statements and back. So in English, we might say a statement such as if P then Q, which means if P is true, then so is Q. And the symbol for this conditional is an arrow, which we see right here, and it's read implies. So in logical statements, we would write this as P implies Q. So, as an example that you could probably relate to, we'll let P be the statement, you won the lottery, and Q be the statement, you could buy a mansion. I'm not saying that you can relate to the fact that you've won the lottery, but you can imagine the following. P implies Q. That means if you won the lottery, then you can buy a mansion. However, notice that we're only stating that when P is true, then so is Q. We're not saying that P is necessary for Q. This is a logical fallacy that trips up a lot of people. So Q could be true even if P is false. For example, let's say you become a famous movie star. You're finally discovered and you make millions of dollars, then you can buy a mansion and you don't have to worry about winning the lottery. So P can be false even though Q is true, and the statement P implies Q is still true. In other words, remember what that statement is. If you win the lottery, you're going to be able to buy a mansion. If you're a rich and famous movie star and you win the lottery, you can buy a mansion. So it only matters that when P is true, that implies that Q is true. Another way to say this is Q if P. It means the exact same thing. So you could buy a mansion if you win the lottery. Means the same thing as if you win the lottery, then you can buy a mansion. It's just a different way to phrase it in English. You might start noticing why it's a little bit confusing to go from a formal mathematical logical structure to English statements and back, because there's so many different ways to say the same thing in English. Just because of the way that our brains process information and things sound more natural or sound nicer the way we're used to doing things. Another way to say this is P only if Q. So this still says P implies Q. Using the lottery example, this would read, you have won the lottery only if you could afford a mansion. So it sounds a little bit different, but you could imagine your friend saying, I've won the lottery, and then you could say, oh, well, let's go buy this mansion. And he says, oh, I can't afford that. Then you might get a little suspicious and say, if you've won or I guess the way that this is phrased, you've only won the lottery if you can afford a mansion. So it's logically, it means the same thing. And finally, because of the previous two statements, Q if P and P only if Q, we can combine the statements to P if and only if Q to mean something slightly different. This means both Q implies P and P implies Q. So the statement P if Q means that P implies Q. So that's the second one here. And the statement P only if Q means that Q implies P, which is the statement here. So you'll see this reasoning, or this language, sorry, a lot in mathematics. P if and only if Q. Let's see. So two numbers are odd if and only if their product is odd, would be an example. And that means that one implies the other and vice versa. Let's look at the truth table for implies. So P implies Q means that whenever P is true, then so is Q. So true implies true is true. You could write the symbol, I guess. True implies true equals true. False implies true equals true. That's like the example we looked at above, where if you become a famous movie star, you can buy a mansion. So it doesn't mean that you necessarily won the lottery, but still winning the lottery would make this true. And a false implies false is also true. So this is a little bit confusing a lot of times when people see this for the first time. If the premise is false, there's no way to really test the claims. You could think of it that way. So a false implies true is true. A false implies false is true. Another way to think of this would be if you start with true premises, you're only going to get true conclusions. So a true can imply a true, but a true cannot imply a false. And that's the only time the statement is false, is true does not imply false. And it can't be the case that whenever the premise is true, the conclusion is false. So you can't say that P implies Q, well, P implies Q is false if P were false, true and Q were false. But if you start with false statements, you're going to be able to derive any sort of conclusion. So starting with a false P, you can derive any sort of Q. You could maybe even find something that's true just by happenstance, and you can certainly find things that are false starting with false premises. So let's see. It looks like I talk a little bit about the scientific method here. So yeah, this is sort of underlies how the scientific method works. We're often noticing or observing some kind of phenomenon Q, and we want to explain what's causing that phenomenon. So we make a hypothesis P and say P is going to cause Q. Well, if we look at the truth table, Q is always true. So we know that Q is some phenomenon that's happened. And unfortunately, if the premise is true, then P implies Q. And if the premise is false, we can somehow also explain Q. So no matter whether we come up with a true or false premise, we're going to somehow use that premise to explain Q. And therefore, we're never going to find the thing that actually caused Q. However, what we do is we try to falsify premises. So what we do is we look for conditions in which the premise is true and the conclusion is false, which is this row here. So we look for places where the premise is true and conclusion is false. And that would tell us that P implies Q is false, or in other words, P does not imply Q. So it allows us to rule out premises. And usually there's only a few premises that seem plausible, right? Like maybe these 4 things could have caused Q, and we try to find conditions in which some of those things hold and the conclusion doesn't hold, and therefore we can rule those out and find what we believe to be the true premise, or the true cause. I also include below the truth table for if and only if, which is denoted with this double arrow. So these things, the double arrows mean logically equivalent. And so if they're both true, then they're logically equivalent, so it's true that P if and only if Q. If they're both false, it's equivalent, so it's true that P if and only if Q. So that's looking at this row. Let me go back to blue. The last row or the top row. The middle 2 rows are false because they're not logically equivalent. If P is true and Q is false, then P and Q are not equivalent, so it's false. And if P is false and Q is true, they're not equivalent, so it's false. So that's the introduction to conditional statements and logic, and I will see you in the next lesson.